For today's 3-minute paper, we'll be exploring the paper by Miro-Vinyals and colleagues titled HaloTag Engineering for Enhanced Fluorogenicity and Kinetics with Styrylpyridium dye. Unlike most recent modifications made to the HaloTag ligand system, where the fluorophore itself is optimized or different fluorophores are explored, here the authors were interested in looking at the protein itself and optimizing the binding pocket to improve binding of a specific styrylpyridium dye through the engineering of the protein. This allows for improved kinetics in binding and also fluorogenicity, as well as avoiding the potential issues that could happen where some fluorophores are not suitable for imaging in mammalian cells. As a result, the authors chose a selection of different mutations at the binding pocket or entry site from the 5VNP HaloTag structure and examined mutations at these regions to explore the binding kinetics and fluorogenicity of their variants in the first generation library. They find that 4 mutations of these ones shown in the top left image were particularly beneficial, including 133C, 175Y, 245A, and 271D being the most important of the 4. And you can see that in the top left figure, when looking at the binding kinetics on the left and the fluorogenicity on the right, 24D had substantial improvements compared to the other variants and the HaloTag 7 itself. In the second generation library, the authors explored the most improved mutant compared to variants that included mutations that were either beneficial or neutral, and other mutations based on the original choice of positions, and found that of these, 271D still had substantial binding kinetics, but HTSP5 had improved fluorogenicity. Prior to acquiring crystallographic data, the author suggests that this 271D variant could engage in electrostatic interactions with the pyridium. And this could be the reason for why they included it in every new variant in the second generation library. In mammalian cell live cell imaging using the HaloTag, as shown here on the right, the authors found that HTSP4 variant was the most fluorogenic in purified protein, exhibiting a 31-fold fluorescence enhancement over HaloTag 7. Additionally, HTSP5 was the most rapidly binding of the variants examined, with a 113-fold more fluorogenicity with the pyrimidinium dye than when binded to HaloTag 7. When obtaining crystallographic data, the authors were able to crystallize the structures of the HaloTag and HTSP2 structures with the pyrimidinium dye, but were unable to crystallize any of the other variants. Despite this, they suggest that the interaction between the dye and HTSP5 could happen because of a number of reasons. And the key improving factors would be potentially found in this variant could be the rate of bioconjugation to the dye, but also the rigidity of the chemical structure itself of the dye, which can improve the intramolecular charge transfer necessary for fluorescence with this small molecule. Overall, The second order rate constant for bioconjugation of the dye with HTSP5 is still lower than that for rhodamine dyes and the HaloTag 7, being 2.7 times 10 to the 6 and 1.9 times 10 to the 7, respectively. But this paper is one of the newer examples of how, instead of modifying the dye itself, the protein can be modified at the active site or in other regions to improve the contact between the dye and the enzyme, thus helping improve mammalian live cell imaging in this case.